Imagine you're standing near a roaring bonfire. You feel its intense heat on your face. Now, take 100 steps back. You'd expect to get cooler, right? It's the most basic, intuitive law of nature. But our own sun, the star that makes life on Earth possible, seems to defy this fundamental logic. For decades, astrophysicists have been fascinated by one of the sun's greatest paradoxes. Its thin, wispy outer atmosphere is hundreds of times hotter than its blazing surface. It's a puzzle that appears to challenge the laws of physics, a cosmic mystery that has endured for generations. But now, thanks to spacecraft that are practically touching the sun, scientists are finally starting to piece the answer together. We all know the sun is hot. It's a colossal sphere of incandescent plasma, a nuclear furnace so powerful it dictates the very climate of our planet. But if you were to ask a physicist how hot the sun is, they wouldn't give you a single number. They'd give you a map. Because the sun isn't a uniform ball of heat, it's a layered, complex engine with temperatures that swing wildly. And the most shocking part of that map is where the temperature doesn't just drop as you move away from its core, it drops, and then suddenly, impossibly, spikes back up to millions of degrees. This isn't just a piece of stellar trivia, it's one of the biggest, most persistent unsolved mysteries in modern astrophysics. The problem laid bare to understand just how bizarre this is, let's start with the numbers we can actually see and measure. The part of the sun we see from Earth, that glowing yellow ball in the sky, is called the photosphere. We call it the surface, even though the sun, being a ball of plasma, has no solid ground to stand on. The temperature here is about 5,500 degrees Celsius, or nearly 10,000 degrees Fahrenheit. That is hot enough to instantly vaporize any material known to man. If you dropped a diamond, one of the hardest substances on Earth, into the photosphere, it wouldn't just melt, it would turn into a puff of gas before it could even begin to fall. But that 5,500 degrees is just the starting point. If you could somehow dig deeper, past the photosphere and into the sun's interior, the heat and pressure ramp up violently. You would first move through the convection zone, a turbulent region where massive bubbles of hot plasma churn and carry heat upward, like water boiling in a pot. Deeper still, you'd enter the radiative zone, where energy travels as particles of light, photons, on a journey that can take hundreds of thousands of years to complete. Finally, you would reach the core. This is the powerhouse of our solar system. Here, the pressure is so immense, over 250 billion times the pressure on Earth's surface, that hydrogen atoms are crushed together to create helium. This nuclear fusion releases the unimaginable energy that makes the sun shine. The temperature in the core is a staggering 15 million degrees Celsius, or 27 million degrees Fahrenheit. That is nearly 3,000 times hotter than the surface. So far, this all makes perfect sense. The core is the engine, and the heat flows outwards, getting cooler as it reaches the surface. This is physics as we know it. The paradox deepens, but here is where the story gets weird. This is where the laws of thermodynamics seem to fall apart. Once you cross the visible surface and move into the sun's atmosphere, the temperature doesn't keep dropping. For a very brief moment, in the layer just above the surface called the chromosphere, it does dip slightly, to about 4,000 degrees Celsius. But then, it starts to climb. And it doesn't just climb, it skyrockets. As you move higher into the corona, the sun's tenuous, ethereal outer atmosphere, the temperature explodes to over 1 million degrees Celsius. In some hot spots, it can reach an unbelievable 20 million degrees, even hotter than the core itself. This is the coronal heating problem. In every other system in nature, if you move away from a heat source, things get cooler. If you walk away from a campfire, you get cold. If you move away from the sun's core, you should get colder. But the sun's atmosphere is a furnace that is orders of magnitude hotter than the surface it sits upon. So, how can we possibly know this? We can't just stick a thermometer in the corona, it would be vaporized in an instant. Instead, we use a technique called spectroscopy. We look at the light that the sun emits. While historically the corona was easiest to see during a total solar eclipse, it is now routinely observed with special instruments called coronagraphs. Different elements glow in specific ways at specific temperatures. By analyzing the fingerprint of this light, scientists can determine the temperature of the gas. They have found iron atoms stripped of 13 or 14 of their electrons, a state of ionization that can only occur at temperatures of millions of degrees. The data is undeniable. The corona is superheated. For decades, the why has remained elusive. But a consensus is forming around a couple of main ideas, both driven by the sun's colossal and chaotic magnetic field. The first theory involves tiny, explosive bursts of energy called nanoflares. Imagine the sun's magnetic field lines as tangled, stressed rubber bands. As they twist and writhe, they can suddenly snap and reconnect, releasing a burst of energy. These are not small events by human standards. A single nanoflare can pack the punch of a powerful nuclear bomb, but on the scale of the sun, they are minuscule. The theory is that billions of these nanoflares are happening every second, all across the sun, collectively acting like a giant stovetop that dumps enough energy into the corona to heat it to millions of degrees. The second theory involves a form of magnetic waves called Alfvén waves. These are ripples, or oscillations, that travel along the sun's magnetic field lines, carrying energy upwards from the surface into the atmosphere. Think of it like cracking a whip. The energy you put into the handle travels all the way to the tip. Recent missions, especially NASA's Parker Solar Probe, which has flown directly through the corona, have provided powerful evidence for this. The probe has detected strange, S-shaped kinks in the magnetic field called switchbacks, which are thought to be related to this powerful wave activity. It seems these waves travel up into the corona and then crash, dumping their energy as heat. While the problem isn't completely solved, most scientists believe that different mechanisms, including nanoflares and wave heating, likely contribute to heating in different places and at different times. If you're fascinated by the fact that the sun's atmosphere is hotter than its surface, and you want more deep dives into the mysteries of our universe, hit that subscribe button right now. We're breaking down the science that changes how you see the world, and you don't want to miss what's coming next. Why it matters on Earth. This might seem like an abstract puzzle for astrophysicists, but solving the coronal heating mystery has profound real-world implications for us here on Earth. The extreme temperature of the corona is what drives the solar wind. The gas in the corona is so hot and energetic that the sun's gravity can't hold onto it. It boils off, creating a constant stream of charged particles that flows outwards through the solar system at hundreds of kilometers per second. Most of the time, Earth's magnetic field protects us from this solar wind, creating beautiful phenomena like the aurora. But when the sun's magnetic activity kicks into high gear, it can unleash a coronal mass ejection, or CME, a colossal eruption that sends a billion-ton cloud of superheated plasma hurtling towards us. If a powerful CME strikes Earth, it can trigger a geomagnetic storm. These storms can overload power grids, scramble GPS and communication satellites, and pose a radiation risk to astronauts. In 1859, a massive solar storm known as the Carrington event was so powerful it caused telegraph lines to spark and set offices on fire. If an event of that magnitude happened today, with our complete dependence on technology, it could cause a global blackout, cripple our digital infrastructure, and result in trillions of dollars in damage. Understanding the corona's heat is a crucial step to predicting these violent solar outbursts and protecting our modern world. The future is solar. Amazingly, the physics behind the sun's greatest paradox might also hold keys to our future. One of the core processes thought to be at work in solar flares is magnetic reconnection. In fusion reactors on Earth, scientists also work with plasma and powerful magnetic fields, but there, magnetic reconnection is usually an instability that needs to be controlled, not a power source. By studying how the sun's magnetic fields store and explosively release energy, we can learn more about the fundamental nature of plasma and magnetism, which could lead to better designs for stable fusion reactors. The sun is the ultimate fusion experiment, and by unraveling its secrets, we are essentially learning how to build our own miniature stars on Earth. There's another surprising angle. The sun's activity isn't constant, it ebbs and flows over a roughly 11-year cycle. During this cycle, the number of magnetic loops, flares, and CMEs changes dramatically, which in turn affects the solar wind that befalls our planet. While the direct link between coronal heating mechanisms and long-term climate change is a complex and debated topic, some research has explored correlations between solar activity, like coronal holes, and Earth's temperature. The star that gives us life is not a static ball of light, but a dynamic, breathing entity, and understanding its atmospheric engine is critical to understanding our own environment. The sun is a place of beautiful contradictions. A place where a 15 million degree core cools to just 5,500 degrees at its surface, only to have its atmosphere inexplicably explode back into the millions. It's a place where invisible magnetic fields act like colossal whips and trigger countless tiny explosions, heating the air to temperatures that should be impossible. Thanks to missions like the Parker Solar Probe and Solar Orbiter, which are bravely flying into this furnace, we are finally piecing together the answer. It's not one simple solution, but a complex interplay of magnetic waves and explosive reconnection events. We are witnessing, in real time, the solution to a puzzle that has baffled science for decades. What do you think is the most surprising thing about the Sun? Is it the sheer heat of its core, or the fact that its atmosphere is so much hotter than its surface? Let me know your thoughts in the comments below. I read every one. And if you want to keep exploring the weird, hot, and fascinating corners of our universe, make sure you hit that subscribe button and turn on notifications. We've got more deep dives coming up, and you don't want to miss the next one. Thanks for watching, and keep looking up.